Uh,
Yeah, go ahead. Yeah,
okay, sorry. Sure. Perfect. Okay, so now what I'll be covering is Distroless, the why and the how, essentially. And you already basically covered this. My name's Arturo Aparicio. People just call me Art because that's kind of a mouthful. It's a bit hard to say. I am a product manager here at JFrog. I have been at JFrog for about 5 years. Before that, I was also in tech. So I've been in tech essentially all my working career. I come from a very technical background, even though I'm a product manager. I love building tools. I love working with developers to build tools. I especially love Docker. We used to rely heavily on virtual machines where I worked at before. When I came over to JFrog, discovering Docker, it opened up a brand new world. It's so much nicer to work with, especially as a developer. Now, before I go into what Distroless is, how you can do it, and all that good stuff, I'll cover a little bit of how we got here to the state that we're at now. So when we're talking about Docker, really, we're talking about virtualization. Docker happens to be the newest iteration, but virtualization has a very long history, and it goes back to the 60s, really. Back then, IBM, when they were using all these big mainframes, back then it was essentially just batch processing, meaning you had one computer, you could only do one thing at a time. So only one person would be able to feed it a job and then get an output. And so if someone else wanted to wait, they had to wait for that one person to finish. So this was okay for certain things, but then when computers started and they were starting to be introduced into things like universities where you had a lot to use the same machine, they needed a solution. So one of the earliest solutions that IBM came up with was to virtualize the operating system. So they did that all the way back in the 60s. And essentially what it did is they had this hardware, the machine itself, and this virtualization system that let it run two operating systems or virtualize the operating system so that two people can now use it at the same time. And that was really revolutionary. It was something of a breakthrough. That machine wasn't very popular, and in fact didn't really even sell. It was more of a research project. But even back then, people saw the need for this virtualization. Now, there have been different iterations of virtualization. Today, we obviously no longer use batch processing, but virtualization has stuck around, and it's been in many different forms. And there's reasons for this. I mean, we know the benefits of virtualization. We know that it encapsulates something. So think about a Docker image. It's essentially encapsulated from the rest of the operating system or the rest of the Docker images. It's reproducible. So something like, think of a virtual machine or a Docker container. You start it up for the first time. It's essentially going to behave the same every time you start it up, right? We're not keeping our state here if we're spinning up a brand new container. And it isolates environments. So just like in the 60s, how they wanted to separate one batch job from another batch job and let them both do what they need to do, this provides isolated environments so that one user doesn't step on the toes of another user. And I think I mentioned I come from a VM world where VMs were the de facto standard. And this was not too long ago. We had our little VMware farm. And that's what people would use. Obviously, with the rise of Docker, that has fallen out of favor. But these VMs were the standard not so long ago. There's a little diagram here about the differences, which I'm sure you guys know, so I won't bother covering that. But what it does boil down to is the containers of today are much smaller than the VMs of yesterday because they have less requirements and we don't need that hypervisor. And there's various other reasons why they're smaller, but it is important to know that essentially the last iteration of virtualization that was popular were the VMs. Now, unfortunately, VMs, it kind of shows that the last iteration was VMs, because when you look at containers today, they look very much like VMs, at least the initial containers that were thrown out there. And this is obvious because people that started to use containers were the same people that were using VMs at the time. So what they did is they essentially took everything that's in the VM that they were using before, they removed the UI, and bam, now I have my container. And it's already a big improvement. It's slightly smaller than the VM at that point. You don't have the UI and has all the advantages of the Docker's containers. But these images are huge. If you create containers like this, it tends to have problems. And we'll cover those problems why. But let's look at the positive. One of the positives is that it allowed those people that had VMs to very easily move over to start using containers, and it allowed the container adoption to come up a little easier. And this led to an explosion of user-created images. Even Docker Hub now kind of, as the Docker community, I'm sure now Docker Hub is suffering from some of those consequences. These very large images that it needs to store and very large images that people need to download, that costs money, costs real money. And it doesn't need to, right? So let me give you an actual example of what I mean. If you're using Python 2.7 and for whatever reason, even though it's obsolete, you do a Docker pull, Python 2.7, the standard version will come with the operating system or the distribution of Debian 10. Now this Debian 10 image, just for you to have Python 2.7, which is a tiny application, you think about what Python actually is, it's very small. It's a few megabytes, right? The interpreter. But you get this image and it's 350 megabytes large, and it has several security issues with it. Okay, so now we covered how containers got to be so large as they are now, and the problems, some of the problems with that, such as they're huge, and I think we covered this. It's slower to download and upload and costs real money, which is why Docker Hub has introduced that rate limiting, and eventually will introduce the storage limiting as well. And really the result is that images have a lot of baggage that they don't necessarily need. And when we talk about this baggage, we're talking about things like package managers, right? If you were to pull any regular old image, you'll more than likely, in a lot of them, they'll contain things like a yum or apt-get, right? Or APK, which you may or may not need. More than likely, you do not. It also contains services. Think about your firewall Ds or other background services, as well as things like tools. Think about your ls, your cd. Unless you're running a shell script, you don't necessarily need those tools, let alone the bigger tools, some SSH or something along those lines, and so on. You might even have, in a lot of cases, editors like VI and, God forbid, Emacs, which itself is like 200, 300 megabytes. So, okay, so now I think everyone can kind of understand that some Docker images that you work with are really big. But you might be wondering, is that really a problem in terms of an individual Docker consumer? You only have to download them once on your machine or on your CI server, and then it's cached, right? So then really, why is it such a big issue? And for us individuals, it's not so much an issue. I mean, it's an issue for people like Docker Hub, where they have hundreds of thousands of people downloading from them. But for us as a consumer, not such a big problem. The problem really for a consumer arises when you need to quickly deploy hundreds and thousands of images, right? Then size becomes a real problem, a real bottleneck. And there's been solutions to actually try to solve this. One of them is Uber Kraken, implemented by obviously Uber. Another one is JFrog Artifactory peer-to-peer. Essentially what these solutions do is they allow the clients that are downloading them to also be peers and be able to download from each other. This is a huge improvement for service-oriented approach where you have to deploy an image to thousands of servers at the same time. Think about Uber updating their services, and they need to do it quickly, and they use containers for this. For them, Uber Kraken is super important because they can't rely on a single point to download all those images. It would be extremely slow. It wouldn't perform as they need it to. I think I talked about this case already, but the case about patching hundreds of servers isn't specific to something like Uber. You could think about companies that are streaming services. Think about your Netflixes, your HBO Go's, all the new ones that are popping up, Peacock. All of those need to respond to things that are on demand, right? Let's say their traffic is ticking up. They need to spin up new servers to be able to handle the load. They need to be able to quickly deploy these servers, and they rely on these types of technologies. And in those cases, each megabyte matters because it's going to be all that much slower to be able to do something. But size is not, in and of itself, it's not just download and storage consumption that size is a problem. Size, unfortunately, also correlates with complexity. Pretty much just more stuff. And unfortunately, having more stuff means more security implications. It's think about having a small house, the equivalent of having a very small house. Only so much stuff can get so dirty, right? You might be able to clean it in an hour or so, but the larger the house gets, the more potential for it to get dirty, or the more you have to clean. The same thing applies when we're talking about Docker containers and their sizes and their complexity. So let's go back to our example of Python 2.7 using the standard Debian 10. If we were to scan it with pretty much any security tool, and in our case, I used Artifactory, and I'll show that a little bit. There are hundreds of security issues, and these security issues are almost exclusively in the distribution, meaning they're not problems with the application that you might install in this container image that requires Python 2.7, but they're just in the base container image that you happen to be using because you need Python 2.7. So there's also an excess of components. There's a lot of components in there. So even if you didn't care about security issues, you probably should. Then there's also license problems, right? The more licenses, the harder it is to audit. And for certain software distributions, that might be a real concern. And even though for us developers, if we're developing something locally and we're running something locally, we care less about security issues or the licenses that it happens to have. But when we're distributing this software or the company is selling this software, then those bugs and those licenses that are not even ours, it's the fault of the base image that we happen to be using, they do become our problem. So that's why this is actually something that matters. So I think I mentioned I would show a little bit. So let me go here. Let me just check the meetup, see we can, okay, good. So this is, here we go. No, that's Distroless. Here we go. This is that one image, and I happen to pull this image from Docker Hub, but I'm storing it here locally on my instance of JFrog Artifactory. And you can see all these issues. And the very top issues that you see here are all related to Debian. You see Debian Buster, problem with Perl, go back. A problem with a MariaDB connector and so on, right? So unfortunately, none of these are really problems with even Python or let alone our application, but they're problems that we'll own just by using this Python 2.7 image, which happens to be, the default in Docker Hub if you happen to pull Python 2.7. There's also tons of licenses. There's 44 licenses for this one particular Docker image. And that's not even considering what happens after you put your own application and its dependencies in it. Here's just a little highlight of what I already showed you. In this particular case, bash is the issue. And you'll see why Distroless would do away with this issue. Okay, so people realized eventually that this was a problem, having these big Docker containers that were pretty much VMs without the UI in them was not an ideal solution for the reasons we mentioned before. They're too big, and by the fact that they're too big, they have more security issues, more licenses that you have to contend with. So there was an attempt to fix this, essentially fix attempt number one, let's call it. And this attempt was basically, okay, build this container like we built it before using basically everything we had in a VM, but take away the stuff we don't need. So we don't really need X, Y, and Z, and so on. And we did that, and because of that, we have smaller base images. So if you were to see Docker Hub, you might see some of them have tags like -minimal or -less and so on. This basically means that they took this approach where they took an existing image and they removed stuff that they thought that wasn't really needed for what the image is supposed to do, in this case, be a Python 2.7 interpreter. Then there was even another approach, which was to use Alpine. So a lot of the images that you'll see in a Docker Hub, they're like based on Ubuntu or Debian 10 or CentOS. Probably not Red Hat because it's commercial, but Alpine takes a different approach. Alpine is a smaller operating system. So that in and of itself is going to save you space. It has a very small package manager. Overall, it has a very small footprint. It's somewhat security oriented, so it's generally more secure. They tend to patch their OS fairly quickly. It does have one downside, and that there's some issues with compatibility, particularly drivers and things like that may not work in Alpine or work a little bit differently. So it's not 100% ideal, but it's something. So here's that same example. We're using Python 2.7, but this time instead of using the default Debian 10, we're using Alpine. And as you can see, it went from being a 300-something image for this Python 2.7 to being a 25 megabyte image that has Python 2.7. So that's already a massive improvement, right? It's more than 10 times smaller. Is that right? Yeah, more than 10 times smaller. It has less security issues. It has less license issues because it has less licenses in general. So a lot of good stuff. It still has some security issues. Here, there's a particular SQLite library that has an issue, but a lot less. Let me go and show you an example. So here we saw this is the Python 2.7, the 350 megabyte one, the bigger one. Now, if we were to go look at the Alpine version, the Alpine version has 24 security issues, only a couple high ones with that SQLite library. The rest are relatively small, right? It also has only one license, which is also a massive, massive improvement. Okay, let me just see how we're doing on time. Okay. So then we will go to the distroless approach. So the distroless approach is, instead of removing what we don't need, we add only what we do need. So we're basically starting from scratch, from something empty, and only building in what we need, as opposed to taking something big and removing stuff. So then that gets us to, so what do we actually need? Well, for sure, you're going to need your actual application, whether you're developing in Java and making jars or war, or you have like a Python script or a Go executable or anything like that. You obviously need your own application that you're going to put in the container. You also need your app dependencies, your jars, your modules, etc., right? So obviously, you don't write all your libraries. You use a lot of third-party ones. You need those. You might need your runtime, right? So if you have Java application, you'll need your Java, JRE. If you're running Python script, you'll need Python, and so on. And then you kind of need whatever else is in between your app and the kernel. But then this begs the questions, how do we know what all of these things are so that we can actually put them in the Docker image? Well, the good thing is that there's one tool that typically knows what all of these are, and that's your build tool. So what don't we need? Well, you don't need a shell. You don't need bash. You don't need CSH or any of those, unless your application is a bash program. It's probably not. So you don't need that. You don't need tools. You don't need things like VI or LS or cat, again, unless you're actually running a shell script or relying on those tools. So then how do we actually build them? Well, there's a couple approaches. I'll be covering two here on how to build these. And one of them is to use existing distroless images as your base with multi-stage build. And I'll cover that, as well as the way that Google rather does it is using Bazel. So the multi-stage Docker approach. This is probably the easiest one, the one most people here would be familiar with. You use a Docker file and you do so in a multi-stage way. So multi-stage was introduced in 17.05 version of Docker, which is quite old now, actually. It's like 2 or 3 years, maybe 4. With this approach, you can use a full-blown image and just build your software and then transfer only the little parts that you need into it. The good thing is Google provides officially maintained distroless set of images. Those images are available in Debian 9 and Debian 10. They come with language-specific images as well. Think about your Pythons, your jars, your Python, Java, Jetty, all of that. There's also compiled languages, runtimes, or imagine if you need to run your Go application and so on, your C++, right? Okay, so let's go ahead and build that. Let me just check and see if there's any questions. Maximize the presentation window. Okay, I think it was though. So. Okay. You guys see this? So this is a multi-stage Docker image. Let's just look at it really quick. Let's just cut it super small. And we're doing, I guess what really makes it a multi-stage Docker image is this from here. And then this other from. That's essentially what makes it a multi-stage Docker image. A typical Docker image has a single from. Now this from in multiple locations has several advantages. I think we cover some of them later on, so I'm not going to talk about it too much. But essentially, as you're taking one image to do your build, to build your application or package it, and then you're taking a different image, which is going to actually be the base image that you're going to distribute and put your application into, and then using that. And I'll show you why this is a big advantage, but let's go ahead and build it. Test 1.0. So it's quick because I had already built it, but we could run it to see that it's an actual full-fledged image. It basically does something special. It runs a Go application that hello world, right? Not something out of this world. But the important thing is that it's distroless and it's super small. So let me show you what that actually looks like. And let me actually open this Docker file. So here we had Golang 113, which we used to build it. And then let me push this image actually. Okay, so we used this image, Golang, here to build it. Wait, give me a second. Where's the Docker info? Here we go. Oh, sorry, some slowness here. Okay, and this image happens to be 300 megabytes, right? And that's what we used to build it. But our image, what we actually produced, let's go ahead and should be here. It's only 9.8 megabytes, right? So even though we use this 300 megabyte Golang compiler, our actual end result, when we put it in a distroless base image, is only 9.8 megabytes. So that's essentially how you're able to do distroless images using Docker. I think we're starting to run out of time a little bit, so I'm gonna skip the base. So I won't show the Bazel demo, but I will cover it right now. Now, there are many other advantages to using this multi-stage Docker build. You can use a single Docker file instead of having to spread something out over multiple Docker files. You can use different images for different parts of your build. For example, you could use one for building it, one for testing it, and so on. This is going to depend on how your build process actually looks like, but you could use them. You could do that all within a single Docker file. You could also use it to change the operating system of certain Docker images. For example, we at JFrog distribute our images, they're Distroless images. And if a customer wants to change the operating system because, say, they have a specific requirement, which often happens if they happen to be running Red Hat and they need all their systems to be running either on Red Hat or using their universal base image, it's very easy with these Distroless images to then just change the operating system. And all we need to provide them is the actual Docker image that we ship, and a little bit of example code of how they would change it with the Docker file. We don't need to actually show them how we build our image. They don't need to build it from scratch. They don't need to throw in the application in there like we do. So it's very, very handy for that as well. Now, the other approach is to use Bazel. Bazel is an open source build and test tool. Like any new tool, it has a learning curve, and Bazel is really kind of different than most other tools. Something along the lines of Gradle, but syntactically very different and less functional. But Bazel is essentially how Google builds images for production. It doesn't require Docker, which is one of its biggest advantage. So you don't need the Docker daemon running or even the Docker client. And you're able to build images. So this is particularly handy for those build machines where you're not able to have Docker installed. You don't need root access either. And the images that it produces are both deterministic and reproducible, as are all Bazel images. Bazel builds, rather. So since I didn't run through the demo, but I will cover a little bit of what syntactically it looks like. It's not very complex, actually, and anything you could do in Docker, you could do in Bazel. You could, for example, pull an existing image. If you need to use it as your container and you don't have it locally, for example, you'll need to go and download it. So you could do that using Bazel, and you express it like this. Which is somewhat self-explanatory. Is essentially the equivalent of Docker pull Alpine 3.8. You have your tag, your repository it's pulling from, and that's it. We had to you don't see the index docker.io or library in this command because they're implied when you're using the Docker client. Those are sort of inherited, right? It adds them in there without you knowing. We can also push images. So after we've built images, obviously you'll need to push it somewhere, a registry of some sort. So here is how you would do that. Again, nothing you would not expect. There's a couple of things I will point out. One is you specify a name. And here, as opposed to specifying an image, like when you do a Docker push, here you specify an image, both of the image name and where you're pushing it to. Here it's different. Here you specify an image which you had to have defined before. For example, if we had pulled this image, we gave it the name Alpine Linux AMD 64. You could then push it, referring to it by this name, Alpine Linux AMD 64. Then you also specify what you would expect, right? The registry that you're pushing it to and the repository. Now to build an actual image, it's not too complex either. The syntax obviously different, but it has all the functionality that you would expect. You specify the base image that you want it to use. You specify a command and an entry point if that is what you would have done in your Docker file, right? Now, one of the most important things, though, is actually adding packages. So what we saw, since we're building this from scratch, if we're using Bazel, particularly if we're using the base, then you need a way of adding packages. And those packages you add like this. Essentially, you say what packages you rely on, and so on. Hopefully your build tool is doing this, because it could be a bit difficult to figure out what you do or don't need, which is why the Bazel approach is a little more complex, but it does allow for even smaller Docker images. Now, before I open it up to questions and all that good stuff, I should point out there are some pitfalls that you might run into, so just be aware now. Because these images are smaller and everything that you don't need you actually need is in them, debugging can be an issue. Especially if it doesn't ship with things like even a shell, so there's no way you could Docker exec into it and see what's going on if you were to run into an issue. So for this, there's Debug Versions. So Google not only distributes those versions I had mentioned before, they also distribute -debug of those very same images. And these -debugs operate exactly the same as the non-debug versions, except that they have the tooling that you would need for debugging. You think about your shell, your editor, and so on. And because of the reason above, it doesn't have everything you would expect. Runtime container file system manipulation is hard or impossible. And by that, we mean you're not going to be able to change something inside a running container unless you mount a volume or something, then you could change that, just because you can't get into it realistically. One other thing is JFrog is giving free shirts for 5 lucky winners. So if you want to enter to win, there is this link here. But don't worry, you don't need to write it down. We're going to post this and send out the link anyways. So you'll have that chance. So 1 in 5, based on. So those are pretty good odds, actually, that some of you are going to get shirts. So let us know. Now, with that said, I'll open it up to any questions or anything. I'll go back to the chat. I'll stop sharing my screen. Here we go.